Hey everyone, so today we're going to be looking at question 1C from the Oxford MAT 2018 paper. And the question is as follows. So we're given two quadratic functions, y1 and y2, and these are given in terms of constants a, b, c, and d. And the question is, for what values of these constants are these graphs going to have exactly two intersection points? So let's try and do a little sketch to see what it's asking us. So if I draw the xy plane here, so one way that this might be satisfied is if we have one of these graphs is a very skinny parabola, so it grows very quickly, and then the second one, maybe it starts higher, but it's shallower, so it grows more slowly. And that's an example where we can definitely see we have two intersection points and they're not going to cross ever again. So the question is asking us, what conditions can we find to ensure that this is always true? So to approach this, we can think about trying to find when these two graphs intersect. And the way we do that is we just set these two equations equally to each other. So if we have ax squared plus c equals to bx squared plus d, then now we're asking for what values of x do these two graphs touch, do they come in contact. So we can try and find when we're going to have two intersection points. So now this is just a nice algebra question, so let's just rearrange. We have a minus b times x squared, if I brought that onto the left hand side, and then on the right hand side, if I just subtract by c, we have d minus c. So now this is a very nice quadratic, we want to solve this. So what we'd like to do is, we'd like to divide by a minus b. We need to be a little careful there, because if this is 0, then we've got some problems. So let's consider what would happen if a minus b equals 0. So let's assume that a minus b equals 0, and let's see where that leads us. So assume that a equals b, a minus b equals 0, then the left-hand side of this equation is always 0. No matter what value of x we take, this is always going to be 0. And for this to be true, we want the right-hand side to be 0 as well. So if we choose the values of d and c so that d minus c equals 0, then this equation is always true. We have 0 equals 0 for all values of x. So that means we have infinitely many solutions. And that's absolutely fine, because we're trying to find when we have two solutions. So if a minus b equals 0, then we have infinitely many solutions, but that's fine. So what would happen if this doesn't equal 0? So the other case, if d minus c does not equal 0, then the left-hand side is always 0, the right-hand side is always non-zero. So this equation is never true. So for any value of x, there's nothing we can choose to make this true. So that means we have 0 solutions. And that's also fine, that's not 2. So just to summarize, if a and b were chosen so that this is 0, then we're left with cases that we don't have two intersection points. So we can just assume that a minus b is never 0. Right? So if we assume this is not 0, then that allows us just to divide through. So dividing through by a minus b, we have x squared equals d minus c over a minus b. So we're trying to solve this, so we can just take the square root. And now the question is, when is this positive, right? So if this is positive, we can take the square root, that's fine. If it's negative, we're not going to have any real solutions. So to get exactly two intersection points, we need this to be strictly positive. If this is 0, then we only have one solution when x is 0. If it's positive, we have 2. If it's negative, we have no solutions. So to have two intersection points, so our answer is going to be, we need d minus c over a minus b to be strictly positive. Right? So this is a condition, so no matter what values of a, b, d, and c, if this is satisfied, then we're always going to have two intersection points. And lastly, I'm just going to do a simplification. We can also write this as d minus c times a minus b is greater than 0. So what I've done is I've literally just multiplied by a minus b squared. And since a minus b is non-zero, this is always positive, so this doesn't change the sign of the inequality. And this actually lines up with one of the answers in the solutions, the ones that they give you. So this is quite interesting because there's a few implications. We see that straight away, none of these brackets can be 0, which means that a and b are never 0, A and B are never equal, and D and C are never equal. So just going back up to our diagram, just to make the connection, it's saying that we can never have A equals B and D equals C. So these two graphs can never have the same y-intercept, and they can never have the same kind of gradient, the rate at which they increase, which means that it rules out us having no solutions, no intersection points, and infinitely many solutions when they line up. So that is the solution to this problem. D minus C times A minus B is strictly greater than 0.